Every developer should know about JSON Web Tokens. A difficult topic, but I'm trying to, break it down into small steps so everyone can walk out of here feeling really confident with their own projects. So, if you look at this simple project, and imagine you want to run this in production, there are already quite a few things that you need to worry about. For example, you want to have your users authenticated. You need to think about access control. You probably want to have some kind of security on your API. Whenever a user does log in, you want them to have some kind of a session so that they don't have to log in for everything they do. You want to have, probably API being used by machine accounts and human accounts. If you do it right, you want to have some role-based access control on it. While doing all this, you need to worry about performance. So all this security stuff shouldn't bother with performance too much. You may need to worry about integrating this API with downstream services. All this while remaining secure and compliant. Well, that can be quite a challenge, and I hope that you will walk out of this room feeling confident that you can build something like this. The superhero of this story is the JSON Web Token. So from now on, I will be calling it a JWT token, but it is short for JSON Web Token. If you look at this, it's a whole bunch of letters. And these letters are what you call base 64 encoded, which is an encoding, not an encryption. So that means that anyone can see what's behind here. You can also see 2 dots here in this document. And that means that there are apparently 3 sections to a JWT token. If you decode that base 64, then you can see these 3 parts of the document. So the top part here in the red is the header. Then the blue part, the second in the middle, is what we call the payload. And in the bottom, there will be a whole bunch of characters representing the signature. If you zoom in to this signature, you will see it's just a bunch of bytes. And, don't worry, I will explain a little bit more about how those bytes got there and why they are useful to you. Before we dive into that, let me quickly introduce myself. My name is Loek Duys. I'm CTO and Cloud Architect at Xebia Microsoft Services in the Netherlands. And we are a consultancy company. So I'm helping a lot of companies around, the Netherlands mostly, but also around the world, doing stuff like this, helping companies get into the cloud in a secure way. Start with why. So why do I believe that you need to know this? First and foremost, JWT tokens are a really popular technology. There's literally billions and billions of sites and tools and apps on the planet that use JWT for access control. So the chances are quite good that you will encounter JWTs in your work as well. And the downside is it's, kind of complicated, so it's easy to do it wrong. And of course, if you do security wrong, then you open up the door for all kinds of, bad things. For example, if you don't do access control right, people can access information they do not own. And if you do not do validation right, anyone can send tokens to your app and just access any data. Right, so these are the 5 things that we will be covering today. First of all, how do you create tokens? Then how do you validate tokens? How can you make sure that a token has restricted access? Different types of tokens that exist around the planet. And finally, how you can protect your tokens against abuse. Let's zoom in to token creation first. This is that JWT token again. And, you can see it has these key value pairs in it. And one of those key value pairs is the ISS one on top. And this means this is the issuer of the token, or where it has been forged or created. And if you look at this token, this is what we call an access token, or a JWT token. An STS is part of an identity provider. So if you look at an identity provider like identity server from Duende, for example, it will have an STS in it. An STS is short for Security Token Service. And well, its sole purpose is to generate tokens. But of course, before you generate a token, you need to know for whom or for which system you want to create a token. So there's, in an IDP, there's also a little bit of account management, usernames and passwords, and sometimes even profile data. And finally, an IDP will also have these things called clients. And clients represent the moving parts of your software. So if you look at clients in an IDP, you will generally have a client inside the IDP for every moving part of the system. So if you have a front end, you will have a client representing the front end. And if you have an API, you will have a second client representing the API. And then, based on those clients, you can add configuration specifying how users will authenticate with those clients and which clients can interact with which other clients. So in my example for the front end talking to an API, you will have one client specifying the front end and how users can log into it. And you will have another client representing the API, and probably you want to have a configuration saying front end is allowed to access API on application level. Right, a different responsibility of an API is the application integration endpoints. So one of those IDPs will always have HTTP-based endpoints with fixed names. The names are specified in the standard. And applications can talk to your IDP in order to get tokens. For example, to do login using one of these protocols like OpenAuth, OAuth 2, and OpenID Connect. So when you do get a token from an IDP, you follow a flow which is called a grant flow. And this is just a set of interactions that you do with your identity provider in order to get a token. Let's zoom into these grant flows for a little bit. There are quite a few, and the one you have to choose depends on two main factors. So first is different user types, for example, user and machine users. And the second is where the host is running. Again, we will zoom into the details a little bit here. So imagine you have a human account in your system, and you want to get a token for that human account. Well, what generally happens is that the user is displayed a login screen. They will provide username, password, MFA, that sort of cool stuff, and then they will receive a token inside their application. And then the token can be used by the client to access a downstream resource server or an API based on the token on behalf of the end user, which is typing in the buttons. And this is how it works in my demo application. So first, from the front end, the user will be redirected to the IDP. So it shows a HTTP screen hosted by IDP. User types in credentials over there, and then the app will receive a token. And finally, the app can send that token to the API, and the API will know, hey, this is user X, and we can validate the token and allow or deny access. It's important to know here that the JWT being returned in this flow will have an identifier that points to the user account inside the IDP. That is the SUB or subject claim. Right, a different way of authenticating to the IDP is a machine account. And in this situation, there is no human interaction. So you have one system, it needs to talk to another system. You need to make sure that that system has credentials in it. So it needs to have access to credentials so it can talk to the IDP on its own behalf, get a token, and access the resource directly. So there's no human involved here. This flow is what we call the client credentials grant flow. And the way this works in my example is the inventory API, it will take its client ID and its secret. It will go to an endpoint, a well-known endpoint on the IDP, get a token, and then access the catalog API using that token, for example. So no subject here because there's no human interaction. Right, I already mentioned that a second factor that determines which grant flow to use is the app host itself. Excuse me. Right, so there are generally two areas in which your app can run. So one is on a web server, which is under your control. And of course, the other one is in a browser or on a computer or a device. The key difference here is the ability to store secrets. So if the app runs somewhere on your own server, it is easy to put secrets there. There are things like key vaults or encryption that you can use on your own hosted servers, which don't apply when the application is running on a device. So the left-hand side, something runs on your server, is called a confidential client. And the right-hand side, something runs on an end user's device, is called a public client. All right, enough talk for now. Let me show you my first demo. Well, it's no surprise that drawing that you saw before, that is the demo app that I've built for you. And well, let's first have a look at the solution itself. Right, so the solution is about tokens. It has that inventory API I was talking about. It has an identity provider. And the identity provider in my demo is identity server from Duende. And I configured it as simple as possible by adding two clients, one for the API and one for the front end. Sorry, this is the API, the inventory API and the front end. And I've configured it to allow certain ways of logging in. And don't worry, I'll come back to that in a bit. And then, of course, we have the API itself. The API will need to know where this identity provider lives, and I chose to do that using configuration. So this URL, it points to an identity provider that runs on my own machine, and this string here, it identifies the system that represents, sorry, the client that is represented inside IDP, client ID. And then, of course, I need to say, hey, use this, this method to configure the identity provider within my API. Again, I will come back to more details later, but this is the way you do it. And the configuration that I'm using for this, I fetched first. And that means that I can say, well, this is where my identity server lives. Then, of course, we have a front end that also needs to know where to redirect the end user to get those tokens. So a very similar pattern is applied here. A little bit more information, but generally it will say, this is where identity server lives. This is me inside the IDP, like the client ID of the front end. And this is the way I want to interact with my end users, and this is the way I want them to get tokens. Of course, there's a little bit code here as well. This is the main method to be used there. You say add OIDC authentication and say, well, I want to have OpenID Connect protocols applied when my user logs in. And again, all of the details will come back in a second. Now, if you run this demo, by the way, this morning demo was totally broken because of a Visual Studio extension that was buggy. So I had a really exciting morning. Fortunately, I got everything back working. So, anyway, so I'm launching my API, I'm launching my front end, and I'm just waiting for Duende Identity Server to be launched. And well, this is my demo. It can only do a few things. So it can log in an user, and I can say yes. Ignore this screen for now. Again, second demo. And now I can see, well, I've logged in as Alice Smith. And when I've fetched data, it will probably work. And this means that I've now talked to my API, fetched some data under the user Alice. And the way this works is by these tokens, which I will show you now. For example, that access token I showed you in my first slide, this is one in real life. And if I decode that base 64, you can see it looks very, very similar to the one I showed you before. So it has a subject claim identifying Alice. It has access to inventory API. So that means that this is an access token I can use for inventory API. Cool. what if I am not a human user? And this is when, of course, we use that client credentials flow. I also have a demo for that. And that uses this HTTP file. So this is just a file that will make a web request based on the content of this file. So if I do a post to my identity server, to this well-known endpoint, providing the proper secret and client ID, I can now say, well, give me a token, and it has responded with an access token for this machine account. So no human interaction here. Back to the slides. Right, so the second thing we will cover is token validation. Well, it's just a string, right? So anyone can produce tokens. So we need to make sure that the token was created by something that we can trust. And this is where asymmetrical cryptography comes in. And, well, I'm not going to do it justice by explaining you it in this way, but if you know the basics of it, it uses two keys. So it has a public key and a private key. And generally what you can do is share the public key with the planet. Anyone can see the public key, and you keep the private key to yourself. And then, because you have two keys, you can do two types of encryption. So first is you encrypt stuff with the private key. And that means that as a receiver, you can access the public key, you can verify it by decrypting that data, and if that decryption works, you know for sure that that information originated at a system that has access to the private key. The other way around is encrypting stuff with the public key, and this is something that you do on the receiving side. So if you want to send something to the server that has the private key, then you use the public key to encrypt it, and then you are certain that only that server, because it has the private key, can decrypt that information again. And this trick is being used in token protection, together with hashing. So hashing is a deterministic digest, so you put a bunch of bytes in, and you will get, provided if it's the same bunch of bytes every time, you will get the same digest out of it every time. So no matter if you hash something or you hash something, if you put in the same data, you will get that same digest out of it. And the cool thing here, it's a one-way function. So you cannot revert hashing. So you can never go back to the original data. And it is very sensitive to small changes, which is nice. So imagine you put in that JWT token and you just change a single bit in that, the digest or the hash will change radically. So it's easy to detect tampering. Furthermore, it's very collision resistant. This means that it's very hard to generate the same hash with two different inputs. And computers generally like creating hashes, so it's easy for them and a small effort for your CPU. All right, so let's combine this now on the JWT token. So the first claim in the header here is the ALG, which stands for algorithm, and it indicates what the sender intended as the signature algorithm for that JWT token. The RS-256 means the R stands for RSA, or an asymmetrical cryptographic algorithm. That's quite a mouthful. And the S part of that algorithm stands for the hashing algorithm, which is the SHA-256 hashing algorithm. So if you combine these two in a clever way, you can create a signature. So what we will do is you create a hash of the header and the payload, and you encrypt that hash using the private key on the IDP. And then you take the bytes that result from it and you paste it underneath the JWT token as the signature. And that means that the receiver of this document can now say, oh, I can see that this specific public key was used for the encryption of the signature, can decrypt it using the public key, then it will return a hash. And then you can reproduce the hash on your own side, hashing the header and the payload. And if these two are exactly the same, then you know at least somebody who holds the private key has created the signature. Don't be fooled by the JWT issuer, by the way. So if I put my own IDP in here and fool your system into validating tokens on my IDP, of course, this whole procedure goes to hell because you're now trusting my IDP. So never use this ISS claim to find out where the IDP lives. And of course, by putting in the signature with the JWT token, it's easy for any recipient, any source code used, like you can use Rust, C#, whatever you want. Anyone, any system that can do cryptography and hashing is able to verify these signatures. Cool. All right, so just a quick recap. So you create a hash of the header and the payload. You encrypt it using the private key inside the IDP, and then paste it on the bottom of the JWT. And then any receiver can fetch the public key from the identity provider, decrypt the signature, verify the hash that results from the decryption with their own hash of the document. If those are matching, everything is okay. So then the front end can send the token to the API. The IDP will provide a public key, and the API can validate the signature, making this foolproof. So a token cannot be tampered with along the way when being sent from the front end to the API. Right. Well, next topic. That is the access restriction. So again, I already said you probably want to have some role-based access control on your API, and this is how you would do that. First of all, you start with the audience. So that's the AUD claim over there. The audience is the intended recipient of your token. So token is not just valid for everyone in your company's domain. It is only valid for a specific target audience. And this is the client ID of the system that will receive the token. Right, but how did the audience get there? Well, the sender will determine what the audience will be. So during one of those grant flows, the sender determines I want to have an access token to talk to my inventory API. So I need to know and send that information to the IDP so it knows what to generate a token for. And because of that configuration specifying which client is allowed to access which other client, you can make this foolproof. Right. If you get a token and you send it to an API, the recipient in this case, it needs to make sure that the audience claim matches what the app itself knows is its client ID. So the way it works in my demo, the front end will get a token with the intent of calling the API. The IDP will issue a JWT token with the API as its audience. And the API needs to check whether the audience matches its client ID inside the identity provider. Right, and now let's talk about permissions. These come in at scope level. So the scope or SCP claim indicates the level of permissions that this token has. So in this case, I'm creating a token for the inventory API. And I intend to do inventory.readWrite. This is a string I invented myself. So this is not part of any standard. So you can put any string you like here. But this string indicates to me in my system that I have read and write access. And you can imagine you can have scopes like inventory.read or maybe inventory.admin, you know. Whatever works for you, this is the way you can add role-based access control by defining all these roles at client level and then saying this app has these roles to hand out, and the requesting app can then say, well, please give me one of those roles. And again, I will be showing demos clarifying this further. Right. So the sender, in my case, the front end, it will say, I want to access the client and I want to access it on behalf of this end user. And then the recipient says, well, for this action to complete, you need to have this specific scope in the token. So you can check for authorization. So the way it works is that the front end will request a token. The IDP will issue a token with specific scopes in it. And then the API can check those scopes and whether they match with the operation that is being executed within the API. quite a mouthful, so let's do a demo and then I can explain it a little bit better. So I will show you my front end. It will request some scopes and then talk to an API, and I will show you how the API validates those. Get rid of this one. Go to my front end, and I skipped over it before, but over here, this is where my front end determines, okay, for every call that I want to make to my API, I am requesting the inventory.readWrite scope. And that means that if my client is configured properly, I will get a token that has that scope in it. And then in my API, I can configure something called policies. And you can see one of those policies here. So, first of all, I will demand that my users are authenticated, so no anonymous access here. And then I can say, well, whenever I'm being called, at least these claims should be present. And I am adding two claims here, so inventory.all and inventory.readWrite. So presenting either of these scopes will allow access to this policy. But this is just a policy, right? So we need to apply that policy to one controller action. And this is the way you do that. So I have a controller here, which is an API endpoint. And I can say at API endpoint level, well, whenever this one is being called, make sure that this policy is enforced. So when this get action is being executed, the system will now check whether the user is authenticated and whether that claim is present in the jar token. Right. I already showed you before, so this is the access token again. So the audience here of the access token indicates the API. And the scope that I got in my token is inventory.readWrite. Then the API will say, well, it has a token, so it's authenticated, the token is valid, and the token has the scope, so I will allow this permission. Right. And then there are these things called token flavors, which is a term I invented myself, so don't Google it. This means the different tokens that you may encounter during your project. Up until now, I've skipped all these other scopes that were in that token, and well, there's a good reason for it, because I want to explain it right now. The scopes I didn't talk about yet are OpenID and Profile. And it turns out that the first one, OpenID, enables an additional protocol on top of OAuth 2, which is called OpenID Connect. And this adds a layer of authentication to the authorization that OAuth 2 already offered us. So OAuth 2 was enough for authorization, but now I'm interested in identity information. So who is the user that is pressing all the buttons? And the fact that I want to know more about this user is what the profile claim here does. So OpenID enables OIDC, and profile indicates I want to have user data returned. But, well, if you look at the token, there is no user data here. So the only thing that is user specific is the subclaim, but there's no profile data here. So where is it? It turns out that there is a second jar token, which is this one. If you decode the base 64 of this token, you can see it's very similar to the access token I showed you before. But this is an identity token. So it has similar claims to the access token. It is a different audience. It has a different audience, which is the front end. So that means it is intended to be used by the front end. It has no scope claims, so it won't be able to access any APIs. And, of course, it has the subject claim, indicating this is a token intended for a human user. And it has all these profile claims. So the bottom, let's say 5, are dynamically determined by my configuration. So I've configured my IDP to return these values whenever profile data is requested. Then finally, there is this last scope claim here, which is offline access. And this is kind of a, well, a complicated name. This means that a client wants to have the right to access a resource whenever the user is either online or offline. So it doesn't need any user interaction to get tokens. And it turns out that we have a third token here, which is called a refresh token, that we can use for that. So access and identity tokens have a limited lifetime, so they are valid for usually about an hour. And in order to prevent having to log in every once in a while, there's refresh tokens. So they can be exchanged for a fresh set of tokens. So if the access token is about to expire, you can use a refresh token to get a fresh access token without user interaction being required. So this kind of enables a sort of single sign-on for this application interaction. So it doesn't work across application, but just for a single app. Whenever you use an IDP, generally a refresh token is not a jar token. It is just a reference token. So this is just a bunch of hexadecimals here, and apparently identity server knows what to do with these bytes. But I, as a mere mortal, I don't know what this information has. So it may be a session ID, it may be, I don't know. There is state inside my IDP that knows, yes, this is a valid refresh token, and I can use it to get tokens, access and identity tokens for this specific client without user interaction. All right, to summarize, we have these three flavors of tokens. Access token authorizes access to a specific system. It has claims about the authorization, so it has scopes claims in there. And generally, it has a short lifespan of minutes to hours. Then there's an identity token. It authenticates human beings, and it will have claims about the end user profile data. And then finally, you have a refresh token, which is pretty much used to get other tokens, and generally has a little bit of a longer lifespan. Right, just to quickly review where these tokens are being used. So an access token is generally sent from the front end to a resource server or an API in order to access resources. An identity token is intended to remain in the front end. It usually stays there. And a refresh token is being sent to the IDP to get fresh tokens. And then there is this thing called user consent. So me as a human being, I want to have some control over what types of data the client can access on my behalf. So I want to have control over that. So maybe I don't want the system to have offline access, for example. Maybe I don't want the application to access my profile data. And the cool thing here is that I am in control. So I can pass consent as a human being. I can say, yes, you can access this information, but you cannot access that information. So even though the application may request profile data, I, as an end user, I can say, that's not going to happen. And this is that consent screen that I displayed earlier and ignored at that time. This is where it comes back. And of course, I have a nice demo to explain this concept further. So what I'm going to do is play around with those consents and hopefully show you what the effect is on well, the system when I don't provide consents. So the first one, I provided all the consents. So it allowed an ID token, it allowed access token with read-write access, and it allowed refresh token for offline access. But if I clear those consents and then go back, log out, so I get fresh tokens. Log in. All right, so I'm not sure if you can read it all the way in the back, but what I'm now going to do is I'm going to say, well, you can't have offline access and you can't have inventory read-write. That means that a refresh token is no longer present, because I, as the end user, I said, nah, not going to happen. And when I show the ID token, the token is, when I show the access token, the token is there, but it doesn't have API access because I did not allow the client to access that API on my behalf. So if I do fetch data now, then, well, if everything works correctly, it should not return data, but an error, and, well, it does. So as an end user, you have control over what you can do. Of course, the same thing applies for profile data, which I'm going to skip because I think you get the concept. Right. Doing quite good on time. Token protection. Well, you've seen me mess around with tokens quite a lot. That means that if I can mess around with them, any attacker can also mess around with them. So you need to make sure that you protect your tokens as well as possible. And, well, for example, whenever you issue access tokens, I do recommend that you have TLS enabled on your identity provider. For identity tokens, make sure you minimize the amount of profile data being returned, because anyone offering their consent will enable systems to access your profile data. And only put in there what's absolutely needed for operational work, like displaying an end user name is probably fine, but bank account numbers should not be in identity tokens. Finally, refresh tokens, protect those because, again, it's just a bunch of bytes, and if anybody gets those bytes, they will be able to get fresh access tokens on your behalf. So the single most important thing you can do here is making sure that a refresh token is only valid for use once. So you use a refresh token and you spend it, and in return you get back a new refresh token together with access and identity. But you need to use that new one to get the next one. And at least this will bring you a detection mechanism for refresh tokens being stolen. So if your refresh doesn't work, you know the original token was stolen somehow. And that means you can block that user account. Right. The best thing you can do, of course, is not play around with tokens at all on the end user's device. And this is the way you would do that. So this is when the backend for front-end pattern comes in. So this is the center system here. Yeah, no, you can't see it, but the BFF thing on my diagram there, that has been added to the mix. So what happens here now is the front-end will log in. The IDP will issue a cookie, so no tokens. The cookie will be stored on the front end, but no tokens will be present in the front end. And then the front end can do an API call using the cookie. The BFF will capture that cookie, take information from it. Probably a refresh token is hidden somewhere in an encrypted form in that cookie, so it can use that to get tokens. And the BFF will call the API on your behalf and then send back the information to the BFF and send it down to the front end. So no tokens in the front end in this case. So you mitigate all that all those problems that you could have when tokens end up at the end user. Of course, I have a nice demo for this as well. So I've replaced my SPA front end from using tokens to using cookies by adding a BFF into the mix. I need to terminate a bunch of stuff. Close the browser. Right, different launch profile. And see if that works. Okay, while this is launching, I will quickly show you the absolute basics of the BFF. So the BFF is just a package that comes with identity server. You can just add it to your project. It will introduce just another reverse proxy or YARP from Microsoft, and then allow you to add routing rules. So my BFF has two rules. It will say whenever an incoming HTTP path has /API in it, send it to the API. And for all else, send it to the front end. And that is enough to get a BFF in place. Of course, you need to configure it with authentication for a little bit. This is kind of complicated, so I will say, well, you need to have this. So add cookie authentication and OIDC connection. So it can exchange cookies for tokens. But this is all open source, so I invite you to look at this back home. Then it should have started. Yep. So I will open up the browser tools and log in. And the key difference here, of course, is when I say I want to log in, I don't want to see any tokens in this environment. Come on. Yep. So when I do fetch data, instead of sending a token, it now sends inventory. It now sends a whole bunch of cookies to my BFF. The BFF is listening, it receives that cookie, and it will say, well, I can exchange that cookie for a token, call the API, proxy the information back to the front end, and now 0 tokens in my front end, and, well, a more secure system. Right. All right, so this is the 5 things that we covered today. If you want to take a picture, that's nice, but I'm not going to cover them all again. All right, just one more slide. And that is, well, thank you all for joining my talk. I hope you enjoyed it. If you want to get access to all the demos and the open source software, please have a look at my GitHub repo. And if you have any questions, we have, well, 10 minutes to spare for that. And again, thanks for joining.